The last type of chemical reaction that we're going to discuss this chapter are oxidation-reduction reactions. Oxidation-reduction reactions, also called redox reactions, involve the transfer of electrons from one element to another element in a chemical reaction. In the reaction, there is always an element that is oxidized, and the element that is oxidized is the one that loses electrons. So oxidation is the process of losing electrons. The reason we use the term oxidation is because the old definition meant that elements that were oxidized would gain oxygen atoms. But the more modern definition expands our understanding that oxidation is a loss of electrons. The second half of an oxidation-reduction reaction is the reduction part. Reduction means that an element gains electrons. Again, the word reduction comes from the old definition where a chemical in the reaction would lose oxygen atoms and therefore be reduced. But we've changed the definition to be a little bit broader so that it includes other elements other than oxygen. An easy way to remember the difference between oxidation and reduction is with the mnemonic oil rig, where the word oil stands for oxidation is losing, and the rig represents reduction is gaining. And as long as you know that electrons are being lost or gained, you can remember the definitions for oxidation and reduction. Another mnemonic is Leo goes Ger, where Leo stands for loss of electrons is oxidation, and the Ger represents gaining electrons is reduction. There are many different examples of redox reactions that you might encounter in your daily lives. In the example with the Statue of Liberty and the iron rusting, you're taking a metal and reacting it with the oxygen that's in the air to create a metal oxide. And so that metal is being oxidized. In aerobic cellular respiration, which you should have learned in biology, the glucose that you eat is oxidized and converted into carbon dioxide, whereas the electron carriers that are involved in that process are reduced because they gain electrons and carry them into the other chemical reactions of respiration. Common reactions involving reduction are then the opposite, where you're taking some sort of ionic salt and reducing the metal ion down to its pure form. In the smelting of iron or aluminum ore, we're removing the oxygen from the mineral that we dig out of the earth in order to reduce the metal down to its pure form of iron or aluminum. In photosynthesis, the carbon dioxide is reduced to form glucose, whereas the water is oxidized to form oxygen. In order to determine which elements are oxidized and which are reduced, we assign oxidation numbers. Oxidation numbers are the apparent charge on each element in a compound if all of the electrons were on the most electronegative element. So it's not the real charge that's on each element, but it's what charge the element would have if all of the electrons were hanging around the most electronegative element. The flasks in the picture contain solutions with different chromium ions. The flask with the yellow solution is sodium chromate, where the chromium has a +6 as its oxidation number. The flask with the green solution contains chromium chloride, where the chromium has an oxidation number of +3. So chromium ions change colors depending on their oxidation state. This is the basic premise of how breathalyzer tests work. The chromium in the breathalyzer test reacts with the ethanol in your breath, and depending on the amount of ethanol, the chromium will change from yellow to blue. Often we represent redox reactions using half reactions. A half reaction splits the chemical equation into an oxidation half and a reduction half. So for example, in the chemical reaction magnesium and bromine combining to make magnesium bromide, I would first need to assign oxidation numbers in order to determine which element was oxidized and which element was reduced. After assigning oxidation numbers, I can see that the oxidation half involves the magnesium, because the magnesium is going from an oxidation number of 0 to a +2, it is losing electrons. And so when I write the half reactions, I show those electrons that are lost on the product side of the reaction. The bromine is therefore reduced. The bromine goes from an oxidation number of 0 to -1, so it is gaining electrons. And because the electrons are being gained, I write those on the reactant side of my half reaction. The processes of oxidation and reduction must occur together, because if one element is losing electrons, those electrons have to be gained by another element. Also, the number of electrons lost and the number of electrons gained must be equal. These two guidelines are necessary in order to comply with the law of conservation of matter, where the electrons are not just being lost or being gained, but rather they are being transferred from one element to the other. In redox reactions, there are also special chemicals called reducing agents and oxidizing agents. The reducing agent is the chemical that causes reduction, and it causes reduction by giving away electrons. The reducing agent in a reaction is normally the reactant that contains an element that has a very low electronegativity, like those elements that are in group 1 or group 2 that have a tendency to lose electrons easily. An oxidizing agent is the reactant that causes oxidation. It causes oxidation by stealing electrons from other elements. Oxidizing agents normally contain compounds that have very electronegative elements, like chlorine, fluorine, oxygen, or nitrogen, because these elements tend to gain electrons in order to become stable. Bleach is an example of a very powerful oxidizing agent. Bleach works by removing the electrons from the dyes in your clothes that give them their distinct color. Now, an activity series of metals is actually in order according to how easily these elements lose electrons. The elements at the top are the more active metals, and these elements tend to lose electrons easily. Because they're losing electrons, they are easily oxidized. Because these elements give away electrons, they are also strong reducing agents, meaning they cause other elements to gain electrons. The lesser active metals, towards the bottom of the activity series, tend to gain electrons easily. If they're gaining electrons, then these elements are being reduced, so the less active metals are easily reduced. Because these elements are gaining electrons from other atoms, they are also known as strong oxidizing agents, because they are causing other elements to be oxidized or lose electrons.